Earlier in flat fading, we have seen the characterization of flat fading, the characterization of envelope of the received signal, the correlation of the signal, and then we define the coherence time and Doppler spectrum when we consider the relay fading condition. And in flat fading, what we consider is we have an ellipse, and the transmitter and receiver, they are present at the two focal points of the ellipse, and all the reflectors and scatterers, they are present on the ellipse. As a result of which, what we get is all the rays that are arriving at the receiver have the same propagation delay. That means tau 1, the propagation delay of first path, is equal to propagation delay of second path is equal to some constant propagation delay tau hat. As if what we are getting is, let's say this is the delay axis tau, and at this tau hat we are getting multiple responses with the same of different magnitude at the same tau. So this is what we defined in flat fading, and this is h t comma tau. And when we take the Fourier transform of this h t comma tau, we get the responses across the frequency. And what we observed is that in the frequency axis, the response is flat over a span of frequencies. So now if we assume that what if we have multiple ellipses? Instead of one ellipse, we have multiple ellipses. We have another ellipse with a propagation delay of tau 2 hat. We have another ellipse with a propagation delay of tau 3 dash, and so on. So now what we need to see is that the propagation delay of this path is not equal to the propagation delay of this path, because it has to travel more distance. So the propagation delays, they are not same, and this propagation delays, that means that this delay we are considering because it can be resolved by the receiver. And this tau 3 dash, why we are considering this? Because they are resolved by the receiver. Anything between tau 1 dash and tau 2 dash may not be resolved by the receiver, so we in general consider the tau 2 dash. So at the receiver, what we are getting is, suppose if we launch an impulse into the system, and this is our delay axis tau, and this is h t comma tau. So we are getting some responses at tau 1 dash. We are getting some responses at tau 2 dash and some at tau 3 dash. So earlier in flat fading, what we were getting is only at tau 1 dash. But now we also have to consider this tau 2 dash and tau 3 dash. That means in frequency selective fading, the delays are different and they are distinguishable. So what are the things that we have studied for flat fading does also applies to the frequency selective fadings, but only thing is that we have to repeat it at different delays. So this is the fundamental difference between the flat fading and the frequency selective fading. So now in case of frequency selective fading, what we can write is t of t comma tau is equal to summation L is equal to 1 to L h of t comma tau L delta of tau minus tau L, where this L represents the number of ellipses, the 1, 2, 3 and so on. And so with every ellipse we have a delay corresponding to that ellipse. And now in each of the delay, for example, in each of the ellipse, we don't have one single path. We have multiple paths coming at every delay. For example, at tau 2 dash, we have this ray, then we have another ray, or we have another ray. So this is basically the summation of n multipaths coming from the transmitter. So how we can write this is summation L is equal to 1 to L, summation n is equal to 1 to n, h of n t comma tau L, delta of tau comma tau minus tau L. So this is the expression for h of t comma tau, where this L is equal to 1 to L represents the number of ellipses. This n is equal to 1 to n represents the number of multipaths that are coming with a particular propagation delay, that is tau L. And now if we want to visualize it further, what we have studied in flat fading, that this ht comma tau is not only a function of delay, but it only fluctuates with time. So what we can observe is, let's say if this is the time axis and this is the impulse received at the receiver at different taus, different delays, then this will also fluctuate with time. So at a particular delay, we have seen that the received signal, the envelope of the received signal is Rayleigh distributed, and the received signal is complex Gaussian distributed. So what we have studied earlier is one of the pulse that is receiving at tau 1 dash, that is varying with time. But now in frequency selective fading, what we are going to study is the number of different pulses at different delays varying with time. And this kind of profile where we see ht of tau as a variation of delay and time, this kind of profile is known as power delay profile. And why it is called power delay profile? Because there is a profiling that happening across the delay axis. So now, what is the fundamental difference between the frequency selective fading and the flat fading? Is that all the delays are different and they are distinguishable. And what we have observed for flat fading can also be applied to frequency selective fading, but we have to repeat it at different delays.